Hello, everyone. Today we're going to talk about solving systems of special systems, I should say, solving equations, solving special systems of linear equations. Okay, so if you remember back, we had some special answers. This kind of falls in the same line when we were talking about solving equations as special answers like infinitely many solutions, um, no solution, and those types of things. So we're going to get started on that right now. So it is section 5.4, chapter 5, section 4, and let's get started. Okay, our daily objective is the following. I can solve systems of linear equations with no solution or IMS. So we can solve linear systems of linear equations with no solution or infinitely many solutions. That's our daily objective. So this is a little bit of a review. We had this back a while ago. So if you have two equations that intersect, that are a system, that's by graphing, you can see the intersection point is the one solution to the equation. So we're focusing on these other two. So you might have a system of linear equations or two equations that have parallel lines. Well, if they're parallel lines, they are going to be considered no solution. So they never touch each other. So two parallel lines, same slopes. Okay, remember that. So if the lines are parallel with the same slopes, we have no solution. Okay. And the last one is a little bit basic, okay, but it is often missed because it's the same line. Once in a while, you'll get the same two equations. Okay, so you've written two equations out, and basically they're the same line. Okay, so when you have that, when the lines are the same, you have infinitely many solutions. Okay, so this would be like the lines right on top of each other. And so we're going to be focusing on these two today with regards to systems. Let's look at example 1. Now, most of this section in example 1, and I'm referring to page 226, it kind of starts out with graphing. Okay, so if you look at on page 226, you can see they used method of graphing to solve the system. But if you can also look at the idea that they have the same slope here and different intercepts. Okay, but if you were to graph this first equation 1, you'd have an equation that looks like this: an intercept at +1 and a slope of 3, 1, 2, 3 over 1, 1, 2, 3 over 1. So you'd have a line that goes up through these blue dots: 1, 2, 3 over 1. Or you could go down 3, 1, 2, 3, 1, 2, 3 over 1. And I could keep going on: 1, 2, 3 over 1. So this would be the line going through equation 1. Now, second equation has a slope of 3. Also, it has an intercept at -3. So at -3, you're going to have a dot. Let me switch colors for this. Go to black. I'd have a -3 intercept. And then we're going to have a slope again of 3. So I'm going to go up 3 to 3 over 1, up 3 to 3 over 1, up to 3 over 1. You can see this line is a line that is parallel to the blue line. Okay, so this line right here in black, the dots in black, are parallel to the lines in blue. Okay, so basically you can see you have the same slopes. Those two lines are never going to intersect. And if they do not intersect, they have no solution. No solution. And your so-called proof of that would be the graph. Okay. So by graphing each of those lines, you can see that they have the same slopes of 3 but different intercepts. One starts at 1 and one starts at -3. So the equation there, you could stop right there. It has no solution, okay? Another method you could use, and the book highlights this, is that you could use substitution. So graphing is one technique, but you could also substitute this y, 3x plus 1, down into the second equation. So let's try that. So 3x plus 1 equals 3x minus 3. And if you have this equation now in the terms of x, you subtract 3x from the right and the left and the right, you end up with 1 is equal to -3. Okay, and that's a little confusing. If you remember back in equations, if you end up with something like this, you didn't make sure you did all your algebra correctly, we just substituted correctly, and you end up with 1 is equal to a -3, that doesn't make sense at all. Okay, so in that case, if it doesn't make sense, it's no solution. Okay, so either you graph and physically see that you have the same slopes and you have different intercepts, and you conclude by graphing, you can conclude that you have no solution, or you could use substitution. And by using substitution, you will see that you end up with 1 is equal to -3, which would also conclude that the equations have no solution. So the next three on your own, we're going to talk about how to get started on them. And I'm not going to tell you exactly how to solve them because they're all these special answers. Let's take a look at number 1. Solve the system of linear equations, check your solution. Now you're going to notice here right off the bat, I have very similar equations. I have slopes of -1 and I have an intercepts that are different, okay? So if you look at the slope of -1 and the intercepts start at different spots, so here you got this line for equation 1. And equation 2 starts up a little higher, about 5, then it has the same -1 slope. And so what we have here is two lines that are parallel. And if they're two parallel lines, there's no solution. So just by identifying 1, the slope, and 2, they have different intercepts, because that's another key. You have to have different y-intercepts to make that conclusion of no solution. Now, if you didn't see this and you just said, okay, let's go ahead and solve this, because we're not going to have a special section on special answers. Okay, so basically you're going to be asked, solve this system from here on out. And so you're not going to, so these are going to be embedded within the test or quiz. So you're going to have to keep that in mind when you're solving for these. So let's say that you just said, well, let's go ahead and solve this. I'm going to take this top equation and use what we probably use the most, substitute. I'm going to substitute it down into this other equation. So I'd have negative of x plus 3 is equal to the negative x plus 5. Well, you can already see by just the way it looks here that you'd end up with, if you add an x to this side and add an x to this side, you'd have 3 is equal to 5. Okay, and 3 is not equal to 5. And so that would tell you it's going to be a no solution. No solution. So either by graphing and physically seeing that it's parallel lines, or by using substitution would be kind of your go-to. All right, number 2. Y equals negative 5x minus 2, and 5x plus y is equal to 0. All right, so first off, let's see if we can graph them together. So if I subtract, this one's already in slope-intercept form, so we can graph that quite easily. It's got a negative 5 slope and a negative 2 intercept. So if I go up 5, 1, 2, 3, 4, 5, I'm going to go over 1. Up 5, 1, 2, 3, 4, 5, over 1. Or I could go down 5. 1, 2, 3, 4, 5 over 1. So the black dots would indicate this line. Second line is not as obvious. I'd probably want to first get it into slope-intercept form by subtracting 5x from this side and from this side. So I'd end up with an equation that is y is equal to negative 5x. Okay, so that has a 0 for an intercept. So I'll just switch colors here. I'll go to blue on this. If I have an intercept at 0, which it is, okay, and I have a negative 5 slope, 1, 2, 3, 4, 5 over 1, 1, 2, 3, 4, 5 over 1. You can see we have two parallel lines. And with two parallel lines, we have a special answer of no solution. No solution. So graphing, or just physically seeing, once you get it into slope-intercept form, that you have two lines that have the same slope, but start at different spots on the y-intercept. Okay. The second way would be to use your substitution. And you have y here. I'll just take that circle off of there. You've got your negative 5x minus 2 is equal to y. You could substitute that down into this equation here. And that would be 5x plus, now instead of y, I'm going to put negative 5x minus 2. And that's equal to 0. So the 5x's cancel each other and you get a negative 2 equals 0. And once again, this verifies that we have a no solution for an answer for number 3. Okay, I should say number 2, that was. So on your own, number 3 now. I'm going to just take this graph off of here because this is pretty much a substitution type of question. You've got yourself 2y plus 10 equals the x. So I'm going to, right underneath there, I'm going to substitute that in for x. 2y plus 10 plus 3y equals negative 1. Okay. So I'm going to start by using substitution. So I substituted in for x. So now we have everything in terms of y. And if I multiply 2 times 2, I get a 4y. 2 times 10, I get 20. Add 3y. And that's equal to negative 1. Now, it doesn't say we're going to get a special solution all the time. So you can see here we have, combining your like terms, I have 7y, because it appears we're going to get an actual answer here, an ordered pair. So if you have negative 1, if I subtract 20 now from both sides, that enables me to have 7y is equal to negative 21. And it appears to me that dividing by 7, I have y is equal to negative 3. So my y is equal to negative 3. So I did not get anything that looked a little crazy there. So we're going to have to just go ahead and find the x. And so happens that x is 2 times the y, 2 times the negative 3. And then we're going to add 10. Add 10, and that will get me my x. 2 times negative 3 is negative 6. Add 10, and you get x is equal to 4. X equals 4. So your answer there is the actual ordered pair 4, negative 3. So as I mentioned before, these problems are going to be embedded within the other problems, the special answer ones. Sometimes you're going to see them. Sometimes you'll get your usual ordered pairs. And that is example 1 with 3 on your owns. The second and last example out of your book on page 227 is example 2. And let's talk about that right now. In example 2, it's kind of a a word problem, I should say. And it says the perimeter of rectangle A is 36. The perimeter of rectangle B is 108. Write and solve a system of linear equations to find the values of X and Y. Okay, so we're gonna have to put together, this is a rectangle. It says this side is 2X. So if that's 2X, I know that this is 2X. And if this is 4Y, I know that this is 4Y. And it says the perimeter, which is the distance around of the rectangle, is 36. 36. So I'm going to have 4y on this side plus 4y on this side. So I'd have 8y plus 2x on the long side plus 2x on the other side. I'd have 4x is equal to 36 for one equation. So 8y plus 4x equals 36. It also says that rectangle B is 108 units. So I'm going to change colors here and go 108. And I'll keep the y's underneath each other. This is 12y on this side. This is 12y on this side. And if this is 6x on this side, I'll have 6x on this side. So the perimeter, according to the information here, we have 12 plus 12 would be 24y plus 6 plus 6 is 12x, combining your like terms. So there's our two equations from the information on example 2. Now, the book does a nice job of talking about using graphing, okay? But I'm going to, and you can look at that on page 227, but I'm going to look at using subs or elimination to solve this. I see this 8 and I see this 24. And I think that we could use elimination quite easily with this 8 and 24. So if I multiply both of these sides by 3, okay, I'd have 3 times 8, which is 24y. 3 times 4 is 12. 12x. And that's going to equal, I got to multiply this side also by 3. 3 times 36 is going to be 108. 108. Now the second equation, I'm just going to leave alone. 24y plus 12x is equal to 108. So by elimination, I can eliminate the y. I saw this 8 and I thought, well, if I made that a 24 by multiplying by 3, I can go ahead and solve this. Well, take a look what happens. I'm going to subtract the 24 y's from each other. I get 0. And this also is 12 minus 12. I get 0. And 108 minus 108 is 0. So I end up with 0 equals 0. So the equation 0 equals 0 is always true, okay? And so that means that in this context, x and y must be positive. So the solutions are all points on the line in quadrant 1. So the system has IMS. So infinitely many solutions for this system. So again, we're dealing with positive distances here, and we have basically the same lines. You can see that once we multiplied by this top equation by 3, we ended up with the same exact line. So with that in mind, we have infinitely many solutions to this problem in example 2. All right, to finish up this lesson now, we're going to do the next 4 on your own. Solve the system of linear equations, check your solutions. So what we're going to do here is we're going to solve it however we can. If we can solve it by substitution or elimination or by graphing, we'll do it however we can, okay? If we get a special answer, we will address it as we go. Now I have the graphs here just in case we want to use them. I have them on the smartboard. But if I look at this first one, number 4, x plus y is 3 and x minus y is equal to -3. I look at these x's here lining up, and I can think to myself, if I subtract these equations, the second equation is from the first, I'm going to have an x minus an x, which is going to have 0, and 1y minus a -1y is 2y. Excuse me there, hold on. 2y. So I got 1y minus a -1y. So to subtract a -1y is to add a y. So I have 2y, and that's 3 minus a -3. So that would be a +6. So y is equal to 3. 2 times 3 is equal to 6. All right, so now you have an actual y. So let's go ahead and plug that y in. You can see that x has got to be 0. So your answer there will be x equals 0, y equals 3. Okay, so you actually found an answer, a solution, and we used elimination to determine that. So we didn't use our graph, and that's fine. If you did use your graph, if you wanted to graph that, you would find that it has an intersection at 0, +3. Number 2, 2x plus y is equal to 5, 4x plus 2y equals 0. Okay, so again, this section is on special answers. And, you know, you're not going to be told that this is going to be either A or B. You're just told to solve it. Okay, so if I look at this, I got 2 and a 4, 1 and a 2, 5 and a 0. A couple ways you could probably use substitution, or you could use elimination. I think I'm going to use substitution. I see this y kind of by itself. So if I subtract the 2x from both sides, I'd have y is equal to -2x plus 5. Now what I have is y, which is -2x plus 5. So I can go down here, substitute this -2x plus 5 in for y and solve. 4x plus 2 times, now instead of y, I'm going to plug in my -2x plus 5. And that's equal to 0. So that's substitution. Let's go ahead and solve it now. Everything's in terms of x. Distributive property will detail at 4x plus 2 times -2 is -4x. 2 times 5 is 10. And that's equal to 0. So what happens at this point is the 4 x's are canceled out, and I get 10 equals 0. We all know 10 doesn't equal 0, so your answer is no solution. No solution. So we didn't use our graph. If you did use your graph in this case, you'd have probably 2 lines that have same slopes. And yeah, if you'd subtract your 4x from both sides and divide by 2, you'd have a slope of -2. But you have different starting points on the y-axis. And that's number 5. So again, you're not obligated to use the graph. I had it here just in case if we wanted to use it. Let's move on to number 6. 2x minus 4y equals 10, and -12x plus 24y equals negative 60. Okay, so this problem here, I see this 2 and I see this negative 12. I see this negative 4 and I see this 24 and I see 10 and negative 60. So if I could somehow get this, use elimination, I can, if I made this 2 a 12, I think we could be in business here. So let's try to work with this top equation. And we're going to work with it by multiplying it by a number that's going to get us a 12. What times 2? What times 2 would get me this 12? And that would be 6. So 6 times 2 is 12. And now we have elimination. So if I have multiply the left side by 6, I got to multiply the right side by 6. And let's see what we end up with. 6 times 2 is 12x. Minus 4 times 6 is 24. And 6 times 10 is 60. The other equation underneath, I'm just going to leave it alone. Negative 12x plus 24y, and that's equal to negative 60. So you probably see what's happening here. By elimination, by setting up elimination, I end up kind of with the same type of problems here. So I'm going to add these two equations together. I get 0x plus, oh, I've got the 4. 0x plus 0y is equal to 0. So I end up with 0 equals 0. And if you have 0 equal to 0, that's always true. And if it's always true, the answer is going to be IMS, infinitely many solutions for number 6. Infinitely many solutions. All points are on that line. Okay, last one on your own is number 7 on your own. Let's give it a try. What happens to the solution in example 2 if the perimeter of rectangle A is 54 units? Okay, so what we did here, I'm just going to, let's just do this. Let's go back to this. They changed the perimeter in example 2 from 36 to 54. Okay, so rectangle A is 54. All right. So the rest of the problem stays the same. 8y plus 4x. So let's write that down. 8y plus 4x equals 54. And the other equation, they didn't mess around with that at all. It is 24y plus 12x is 108. 24y plus 12x is 108. 24y plus 12x is equal to 108. 108. So they just changed the one rectangle to 54 units. All right, so let's go ahead and see if we can solve this. I see the 8 and 24 again, and let's work with elimination to solve that by first multiplying the equation by 3 on this side and also on this side by 3. Okay. So 3 times 8 is 24. And 3 times 4 is 12. And that's 12x. And 3 times 54, though, is, let's see, 3 times, that's 150 times 4. Okay, so 162. All right. The second equation, I'm going to leave the same. 24y plus 12x is equal to 108. So if I subtract the 24y's from 24y, I have 0y's, 12 minus 12, I get 0. So I have all on this left side, I'd have 0. And if 0 is equal to 162 minus 108 is going to be, let's see, that's 42, 52, 54. 0 equals 54. So as you can see there, we have no solution. So by making this change from rectangle A to 54 units, you end up with a no solution problem. So there's no solution. It does make a note here too in the book that these equations are actual parallel lines with different starting points. All right, so what do we conclude here? We have infinitely many solutions and no solutions to look out for now in solving systems of linear equations. So we know that we can come up with one solution. We've done that by substitution, or we've done it through elimination. We've done it through graphing. Now we're looking at no solutions, and we're looking at infinitely many solutions. So if you get something crazy like 0 is equal to 54, you're going to have a no solution problem. If you get some answer that has a case where you have 0 equals 0, it'd be IMS, infinitely many solutions. Basically the lines are the same. And you keep an eye out for those types of problems. So hopefully you found this beneficial today, solving systems of linear equations. And I look to see you soon. Thanks again for listening. Have a great day.